So, hello everyone, my name is Kevin Koch and I'm from the Technical University of Freiburg in Germany. I'm a PhD student and today I want to talk about the effect of the impact pulse on the dynamic fracture toughness behavior of high-strength steel and nodular cast iron. First, a quick look at my outline. First, I will give some motivation for my presentation and will talk about some causes that lead to an incomplete energy conversion in dynamic fracture toughness tests. Then I will talk about my materials, which we investigated, and about the test setup, which was used for the fracture toughness tests. Then I will continue and give some of the most important findings in the tests, and which lead to some energy conversion in fracture toughness testings, and what kind of impact they have on our test results. At last, I will want to conclude my presentation. So first, compared to static tests, in dynamic tests we have to take into account inertia effects, which can happen due to the increased loading rates, which means that the part of the energy is absorbed by the components. If we take, for example, the pendulum impact test, where the impact energy prior to the test is resembled with E0, after the impact, the specimen absorbs a part of the energy. The energy which is absorbed and dissipated can be estimated by the load line displacement, for example, measured at the top. However, part of the impact energy is also absorbed by the components, such as the support or the top. Another reason for energy losses can be the plastic deformations in the Hertzian contact between the sample and the top, or the sample and the support. And this has to be considered when calculating the dissipated energy in the test. Otherwise, the energy dissipation by the specimen is overestimated, which can lead to an overestimation of the J values which are needed for the fracture toughness calculation. Well, this is known for years. However, usually those effects are more significant at high impact energies, but also those low impact energies are needed to calculate the J values for the crack resistance curve. And this is exactly what we focused our research on. So let me tell you something about our investigated materials. First, we used a nodular cast iron which has moderate strength and Young's modulus, and our second material was a high strength quenched and tempered steel with a martensitic structure. It shows a very high strength and a high Young's modulus. So this is the test setup we used for our tests. We used an instrumented pendulum impact test machine. You can see the test setup here on the right. We carried out our tests in the low blow test manner and at very low impact energies to guarantee elastic loading of the specimen. The impact energy of the top is varied by the displacement angle of the pendulum alpha 0. We used Sharpie specimens with the given dimensions for the tests, and the specimen is placed on the support. The support itself is connected to a steel base, and the steel base is then set on a concrete foundation of high mass. In the test, the displacement was measured at the top with a laser, and the displacement of the top corresponds to the displacement of the specimen, which is later needed for the energy calculation. Here you can see the top view of our impact test setup. The force is measured with strain gauges, which is located at the top. And also we wanted to measure the displacement of the support in our tests to then calculate our energy, which is dissipated by displacement of the support. Also, we varied our specimen geometry in terms of crack geometry and notch geometry to investigate the effect of the specimen compliance. So let me give an overview over our test results. So first, we investigated the behavior of the support in elastic tests. We recorded our force and our displacement of the support over the time, and we could see that first the support still shows a significant displacement after the test, and also that for both materials the displacement increases with our force. Our area under the graph corresponds to the dissipated energy by the support, and the effect is more significant for the steel, which can be described by the higher strength level of the steel. We then repeated the test for different impact energies, and we could see that the support displacement increased with our impact energy for both materials. Then we did the same and investigated the displacement of the top, which corresponds to the plastic deformation of the specimen. And we could see that the displacement of the top increased with an increasing force. And also we could see that the effect is much more significant in cast iron compared to our steel. This can be described by the lower strength level of the cast iron, which leads to a higher plastic deformation in the Hertzian contact, and can also lead to small plastic deformations at the notch tip. Also, we repeated the tests for a different notch geometry, and we could see that the displacement of the top increased with an increasing impact energy and depends on the material as well as the specimen geometry. At last, we performed dynamic fracture toughness tests with pre-cracked specimens with an A to W ratio of 0.5. And we considered the results of our elastic tests. So we could correct our force displacement curves. Actually, the black curve with the higher displacement in each diagram is the raw test data, and the colored curves corresponds to our corrected curves. So next, we calculated our dissipated energy for the specimen via the area under the curve. I have to say that for the steel, we did not observe a significant crack growth, so we just calculated the energy until the force maximum. And what we could see from this is when we calculated the J value from the data and from the corrected data, we could see that there's a deviation. The deviation is much more significant for the steel specimens, and also is affected by the impact energy, which is shown here. This means that due to the inertia effects that occur in the test, we overestimate our J values, which will then result into overestimated fracture toughness. To conclude my presentation, we observed that energy losses in dynamic fracture toughness test could be investigated and identified by deflection measurements with a laser. And these inertia effects and also the plastic displacements occurred at low impact energies, and they led to an incomplete energy conversion. Our first main factor was the elastic displacement of the support, which increased with impact energy and also depends on the test material. Our second factor was the plastic deformation of the specimen, which increased with impact energy and also depended on our test material and the specimen geometry. And I have to add that these effects may be specific for our test setup that we used. At last, I want to thank the German Research Foundation for the financial support of the investigations, and I will thank you for your kind attention. Thank you.